This paper does not prove a damned thing. This study is not capable of informing on cause and effect. This paper's methodology is unable to inform on the question. They modelled what they would expect to occur, given their framework, ergo they've programmed their computer program to spit out exactly what they would suspect it would do based on their underpinning theology. You can't objectively prove objectivity. Let's see if we get anything other than opinions. James, I thought you were a scientist. Right, hello everyone. Thanks for joining me once again, where we are dealing once again with James de Nicolantonio, who is patently, as you'll see, in full cope mode. This, for those that haven't been following along, is a young man without the courage of his convictions to actually front me for a debate on this topic. Instead, it's backwards and forwards videos. Well done on your latest video, James. It's got, as of this morning, 234 views in 24 hours. Good work, son. Hopefully this video will get many more than that. Let's have a listen to James's latest dig at me in the title of this video, which is The Takedown of Bart Kay and the Stewart Model of Acidosis. So let's see, staff, whether or not James achieves the lofty goal of taking me down, because he's already had one crack at calling a video taking me down, to which I've responded and it seems like he didn't. Now let's see if he's got it done this time, shall we? James.
This is a paper published in 2009 that disproves the Stewart approach.
In fact, James does no such thing. Did you actually read the paper at all? Because, no, it doesn't do that.
It's an experimental disproving of...
No, it isn't. The first part is sort of pseudo-experimental in a way. What they've done at one point in this paper is to compare some numbers that they generated using a computer model of chemistry, as they see it, and some laboratory observations to see whether there was agreement to an acceptable level between their model's output parameters and what was actually observed. Okay, so it's kind of a little bit experimental. So if there is a proving of anything in this paper, James would need to tap the relevant data set in this paper, because proof is litigated empirically in the sciences. That's what we need to keep our eyes firmly on throughout this presentation today, staff. Does James at any point tap any numbers that proves what he's saying, while voluminously saying proves and proves and proves throughout his little talk here?
Of the theory, and I'm going to cover this paper in the highlighted text below.
So, in other words, what you're going to do is cherry pick some parts of this publication, highlight those, and read them out. Okay? Let's hope some of the things that he's highlighted are the numbers that would prove his point. Keep your eye on that.
But the paper is titled A Critique of Stewart's Approach, the Chemical Mechanism of Dilutional Acidosis.
Right, so that was actually your first clue, James, and you seem to have missed it entirely, unfortunately. Right after the word A, you'll see the next word is critique. So this is somebody's opinion, isn't it, James? Otherwise, it would have been entitled The Proof that Stewart's model is incorrect in some way. See how it's not titled that? Interesting, isn't it? So we're starting out with opinions. Let's see if we get anything other than opinions.
Published in Intensive Care Med, so anyone can look this paper up if they...
Yes, I did. And it was a rip snorter of an afternoon reading through this absolute banger of a comedy piece. In short, great story, more emphasis was needed on the dragons, and for Christ's sake, at the end of it, let's not just all sit down and have a discussion about who should be king, after all that killing and sex and stuff. Right.
So in the classical dilution concept, metabolic acidosis after resuscitation with large volumes is attributed to the dilution of serum bicarbonate.
Correct. That is what they attribute it to, yes.
However, Stewart's approach rejects the explanation and offers an alternative one that is based on a decrease in the strong ion difference.
Not strictly correct, in fact. Also see how these statements are the opinions of the authors of this paper, because we haven't seen any numbers as yet. Yeah, no, that's not a competent assessment of what Stewart's model really does. In fact, the fully developed, mature Stewart model that still bears his name has been contributed to since the time of Stewart by other authors who have helped to refine the thing and bring it into its full context in the objective reality in which we find ourselves. And that full model suggests to us that with regard to pH and a number of other things, there are 4 and only 4 control levers. And if you want to have a predictable effect over the outcomes, you need to, I guess, actuate one or more of the controls, of those 4 controls, in the right direction collectively, and you need to also exert control over the ones that you're not actively manipulating as well. Le Chatelier's principle, basically. So, no, the Stewart model would not suggest that the reason for the pH change is a change in the strong ionic difference in this case. The model would not suggest that at all. It would suggest that that lever, the strong ionic difference, is still one lever of 4 that all have an effect simultaneously. Ergo, what you say about what the Stewart model would suggest from this point forward in this paper is based on an understanding that we now have that these authors do not understand the model that they're critiquing in their opinion piece. Oh dear, James, I thought you were a scientist. I hope this gets better.
This mechanistic explanation is questionable for principal chemical reactions. The object of this study is to clarify the chemical mechanism of dilutional acidosis.
Goodness, it's a real crying shame then that this paper's methodology is unable to inform on the question. Again, James, did you read the thing carefully at all?
Through experimental data and simulations of various dilutional experiments.
Right, so actually, mostly it's through computer-generated models that they're making assertions, not actual measurements. The actual measurements such that were taken were comparative corroborative, supposedly. We'll see if they were or not at some point, though, I'm sure.
As well as theoretical and chemical considerations were used.
Right, okay, so what they're saying is they modelled what they would expect to occur given their framework, their existing construct within which they are running their field of practice. Ergo, they've programmed their computer program to spit out exactly what they would suspect it would do based on their underpinning theology, their construct. Okay, if experimentally observed phenomenon match the model's predictions, then the model is complete, and I have to concede that whatever is being suggested here might be right. But first we need to see that the experimental numbers, in fact, match. Because if they don't, then we can say, so your model is incomplete, as is your understanding of what's going on here. I see. And then, we've dealt with it. Right, stick around to the end and see if that's what the case is.
The results were the key to understanding the mechanism of dilutional acidosis lies in the open CO2 bicarbonate buffer system, where the...
Do you see, James and others, how that statement there results, the key to blah, 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 do you see how that's just an opinion statement? Why do I say that? Well, which number are they referring to there that they've produced? Which result are they tapping for that conclusion? I don't know.
The buffer base bicarbonate is diluted, whereas the buffer acid is not diluted.
Yeah, but there are several fundamental errors of interpretation there. What else can you say about that? That's an opinion. Show us the outcome statistic that underpins that opinion.
Neither the principle of electroneutrality, nor a change in strong ion difference, nor increased water dissociation plays a mechanistic role in...
Well, this study has not been able to establish that is the case. So there is absolutely nothing to underpin that conclusion. We'll get to the details of why that is in a minute or two. Relax.
In this dilutional acidosis. Stewart's approach is valid at the mathematical level, but does not provide any mechanistic insight.
Well, that's true of everything, James, including the mathematical model that describes your objective reality. It's a set of equations, quantum physics and stuff. You can't objectively prove objectivity, physical existence. So that statement there provides no validity, no utility, I should say. There's no utility in that statement.
So I'm going to go...
But what it does actually do is give us an admission there that the model is valid mathematically. Oh dear, it does match with what we would observe when you actually correctly apply the thing.
Go through how these dilutional studies prove the Stewart model incorrect.
Again, James, I thought you were a scientist. Had you read this paper, you wouldn't be making such ridiculous bluster. This paper does not prove a damned thing.
That strong ion difference is not causing the increase in protons.
No, this study is incapable of informing on that question. Ergo, concluding anything about it on the basis of this paper is a falsehood. It's fallacious. I like the word fallacious. Do you?
We'll cover in detail.
Let's say it together. Fallacious. Well done.
detail what actually is doing that?
No, this study is not capable of informing on cause and effect of what is causing what in any chemical equilibrium system of any kind, actually.
And that this approach is incorrect.
It's not incorrect, James. Still. Did you see just a few minutes ago where you actually pointed to the bit where they said, well, actually, this thing mathematically is correct? Whoops.
And the dissociation of water is not what is leading to an increase in protons due to the strong ion difference.
That's not what Stewart's model claims. The fully mature, fully developed model. It never has claimed that, James. Stewart may have said that at one point. It was Stewart that started the fully developed model back when, in the 70s, as it turns out. It still bears his name because that was the linchpin key to the understanding of this thing. Since that time, it's been put into its context and objective reality so that we know how it all works. And a mathematical sum has been provided which matches absolutely with observation. Absolutely. Every time. Because the model is correct and complete, and it's based on an understanding of physics, which neither James nor the authors of this paper seem to possess for some reason. Stunning stuff.
So objections have already been raised on the mechanistic explanations of the Stewart approach.
So none of the objections have held up. It's still mathematically correct and absolutely correct on every occasion.
The physicochemical validity of its mechanistic explanations has to be proven experimentally.
Well, it has been, by being correct, unassailably, every time. And still, James, proof? Prove you exist. Shall we wait for that?
This will be done in the present study on the basis of the mechanistic analysis of dilutional acidosis.
That's just delusional, James. If you read the paper, you'd understand how delusional that statement is. This paper does no such thing. This paper informs us in no way whatever on cause nor effect of any issue. What it does do is give us an opinion.
Let's go in here. The context of dilutional acidosis. Stewart's approach would argue that the proposed bicarb dilution cannot cause the observed metabolic acidosis because bicarb is a dependent variable.
There you go. Correct. And based in physics, as we understand it. Fabulous. What's next?
Moreover, it was argued that blood acids and bases are diluted equally, hence dilution does not preferentially affect bicarbonate. So therefore, from the Stewart perspective, an alternative explanation for dilutional acidosis needs to be developed.
And it was, but not by Stewart by himself. It still bears his name, and rightly so. But that's not the point here.
His main explanation is based on the strong ions and the maintenance of electroneutrality.
That's the key that Stewart provided us with, that we were then able to go, we get it now. Yes, but it's not what you think it is in terms of being some kind of causal agent here, James. It's one of 4 control levers which must all be manipulated in some way at once in order to get a predictable result.
It was believed that positive or negative charges influence the dissociation of water. In the context of dilutional acidosis, this means dilution of plasma by water or another solution with a strong ion difference of 0 decreases the strong ion difference, diminishes the surplus of positive charges. However, the decrease in strong ion dissociation demands compensation by a positive charge. This is suggested by increased water dissociation with the generation of positively charged protons. This newly generated proton then causes acidification of the solution, according to Stewart's theory. The objective of this study...
That's a very cursory, very poorly developed C- level interpretation of the model, actually.
...was to clarify the chemical mechanism of dilutional acidosis.
Again, it's sad, crying shame that this paper's methodology is incapable of informing upon that.
Particularly, we wanted to determine whether the strong ion difference-induced increase in water dissociation causes dilutional acidosis, and whether bicarb should be regarded as a dependent or independent variable.
Well, there you go. So it's a shame that this paper is incapable of answering any of those questions by its methodology.
Finally, this analysis will be used to clarify several misconceptions arising around Stewart's acid-based approach.
You mean, finally what we'll do is provide you with our opinions on what the outtake or uptake from this paper should be. But James, we're still waiting for you to tap any of the numbers that would support this.
Studies based on simulations of dilutional experiments. Simulations,
you say. Good.
Theoretical considerations and in vitro experiments.
Yeah, well, sort of. Mixing things together in test tubes and measuring some levels thereafter to see whether that matches their model that they've provided.
So they did a bunch of different dilutional experiments using saline, some using a closed...
They did 4 experiments, in fact, James. They did a number of simulations, none of which were experimental because a computer simulation will do exactly what you tell it to. 4 of their simulations have been tested for validity by way of an experimental data set to underpin, is our model correct?
System, others an open system in regards to, so basically, reactions could occur in regards to CO2.
Right, so they've attempted to control one of those 4 control levers in certain circumstances by allowing or disallowing the solution to react with carbon dioxide at a given partial pressure.
And they all...
And is a word that still only has one syllable, A-N-D, and.
Also, all the solutions were constructed and pH calculations were performed as standard methods of chemistry.
Right, so according to the model that you already believe and support, you've put a computer program together and you've told it to behave according to those laws as you see them. And what's your point? Because it will, won't it? Goodness gracious. We're doing science here, though, kiddies. This is how we're doing science.
Using chemical equilibrium equations, mass and charge balances, and then also in vitro experiments were performed for the simulations, delusional simulations of 2 through 5.
Right, so they did 4 experiments to see whether those 4 conditions results matched what their model would suggest should have occurred.
So let's just basically get to the punchline here.
All right. Well, hang on. You've gone to discussion. Where are the results? James, this is a paper that absolutely proves me wrong. Remember? What numbers prove me wrong from this paper? Goodness gracious. James is a great scientist, though, everybody.
We found that the key to understanding dilutional acidosis lies in the open CO2 bicarb buffer system.
All right. That's an interpretation. That's an opinion. Simulation 2 and 4. We'll get to simulation 2 and 4 in a bit, okay? This paper won't do, though. You're going to love this. Stick around. Seriously.
Where the buffer base is diluted, whereas the buffer acid is not diluted.
Yeah, see how that's an interpretation? There are no empirical outcomes of any experiments given there in that discussion statement. It refers to simulations 2 and 4. But where is that? Stick around.
PCO2. The categorization independent and independent the categorization in dependent and independent variables depend on the system, and bicarbonate can be regarded as an independent parameter.
Do you see how that's an opinion? Because there are no numbers there. Do you see that, James? You would have needed to have shown us the numbers.
Stewart's strong ion approach does not provide mechanistic insights into dilutional acidosis.
Well, I disagree entirely, and so do many others, James. Right, so we found that we had some opinions, and afterwards we still had some opinions, and here's what they are, referring to a data set. We'll look for that in a minute. Right, go on, James.
I'm going to cover a few other things here, but this study, these dilutional studies and these in vitro experiments are proving that bicarb actually should be regarded as an independent variable.
No, they're not, James, at all. Completely false statement. Did you read the data, James?
Remember, Stewart said it is a dependent variable. So
it is, still.
These experimental studies prove that is incorrect.
No, they don't, James. There are no experimental studies that have ever been done that have proven that incorrect in any way, shape, or form. No.
That bicarbonate is an independent variable.
No, it isn't.
And then I'm gonna show you basically how the other aspects of Stewart's theory is incorrect.
Well, you haven't shown us how the argument you've just made was correct. You've just parroted somebody else's opinion. We haven't seen any numbers, James. None.
If we now regard living humans, we also have to consider organ functions as secondary processes, such as renal or respiratory compensatory mechanisms. Can we really expect Stewart's approach, which is based on a mathematical model of a physical-chemical system, to clarify the mechanisms of dilutional acidosis in vivo?
Well, why wouldn't it? Because actually, when you add a layer of comprehension overlaying the mathematical model, which is still absolutely correct on every occasion, James, still, you then understand that there are 4 simultaneous control levers that must be manipulated in some way, either held constant or moved in one direction or the other. And then you understand that the physiological processes overlying that model are the things, the physical means by which the physiological mechanism exerts its homeostatic control via controlling those 4 faders. And yes, the model still works. The statements of the model, the mathematical statement of the model remains correct, even if you don't understand physiology and you don't think about the lungs, the kidneys, any of that stuff. Still works.
Coming back to Stewart's approach and the physicochemical level of dilutional acidosis, we have to identify all blood plasma components participating in acid-base equilibrium and linking them by chemical equations and equilibrium constants.
Yes, and that's what the model does.
The relevant acid-base components in human plasma, dissociation equilibria, and equilibrium constants are well known and characterized.
Yeah, see, that's the mistake. That's the fundamental flaw there, James. The values to which you refer, they're not constants. They're called constants, falsely. They're conceptualized, falsely, by many as constants, and they have a textbook value. However, James, they're not constant. They're variable. They're yet more independent variables under the exerted control of those four simultaneous feeders. James, still.
Enables theoretical simulations of the dilutional processes. In vivo or in vitro dilutional experiments are not absolutely necessary to clarify the underlying chemical mechanisms. Nevertheless, data from in vitro experiments for some simulations are provided to support the theoretical data.
Well, where? Because it's not in this paper, James. The results are not provided in this published piece of work, let alone the corroborative data set from the data collected in vitro. So this paper doesn't prove anything, does it? This paper is an opinion piece that talks about some data which is not included in the paper. You can read through the paper yourself, boys and girls, to check me on that. It's not there. We'll get to that in a minute.
In all simulations, alkaline solutions were diluted by a neutral, more acidic solution. Except in simulation 1, all solutions were buffered. Simulations 2, 3, and 5 contained an open CO2 bicarb buffer system, whereas a closed buffer system was used in simulation 4. Furthermore, in all experiments, it could be clearly shown that the change in strong ion difference is only an algebraic necessity, or a marker of dilution, but has not an active or causative role in the mechanism of dilutional acidosis.
But the data doesn't show that, though, James, at all. It's incapable of informing on that, because this study failed to control all four control levers, betas, in any one of the conditions they tested. Whoops. There was always a degree of freedom that was allowed to take precedence and have an effect over the actual outcome situation. Given that you do not understand the cause and effect contributors to the outcome here, you cannot possibly build a model which would correctly predict things. Ergo, your model is incomplete, and we'll get to the data soon. Promise.
Again, disproving now that the strong ion difference is not causing acidosis.
No, it's not proving that at all, James. Complete nonsense.
These experimental studies.
And Stewart's model doesn't suggest that it is the cause. It suggests it's one of four, remember, still?
Are disproving now, not just that bicarb.
No, there's nothing here that's disproving anything, James.
Is a dependent variable, which these studies proved it was independent.
No, they didn't, James, still.
It's also proving that the strong ion difference is not what's the actual causative mechanism of the acidosis.
No, you said that already, and it's still false. It's not correct. This paper is not proving that.
Just proving another part.
No, James, remember this paper doesn't actually publish any of the outcome data set at all. So this paper does not prove anything. This paper is a series of opinions written by its authors. I wonder why they didn't publish the data, James. I wonder why this is published, given that there's no data. Isn't that incredible? Which editor allowed that? That would be stunning to find out. Anyway, carry on.
Of Stewart's theory. For example, in dilutional acidosis, a decrease in strong ion difference, or hyponatremic acidosis, can be found. However, this does not mean that low serum sodium concentration is the cause of the acidosis.
And the Stewart model doesn't say that it is. It says that is one of four simultaneous control levers, James. Still.
Analogously, a hyperchloremic acidosis can have several causes, but is not caused by chloride. Chloride is not acidic. The causes and the compensation mechanism.
Well, when you understand the Stewart model and the reality of it and the fact that it's based in physics as we understand it, James, you'll understand that it's quite correct to say that increasing the concentration of negative ions in a solution will tend to draw out more protons from the water, ostensibly, in order to maintain electroneutrality. So a meaningfully increased concentration of chloride absolutely would tend to exert that influence over the equilibrium, the equilibria, the four-lever system. Maybe I should stop drinking coffee.
Mechanisms of acid-base disorders can only be explained by the clinical situation and pathophysiological considerations, not by a mathematical formula.
Well, that's not true, James. They're not mutually exclusive. The mathematical formula is correct, demonstrably correct, absolutely correct, and invariably correct every time, is what that means. You do not have to understand physiology to get the right answer. You have to understand mathematics quite a bit. That could be a problem for you, James. But when you understand that the mathematics is correct, then you'll know which physiological thing to intervene or manipulate in order to manipulate 4 levers together in the right way to achieve the change that you're trying to achieve. Okay, pretty straightforward.
Summary and conclusions.
So, summary and conclusions, not a single data point described or discussed, James. Good.
The chemical mechanism of dilutional acidosis when focusing on blood plasma is the dilution of an open CO2 bicarb buffer system where the buffer base bicarb is diluted, but not the buffer acid.
Okay, well, number 1, carbon dioxide gas is not an acid, still. Number 2, the data in this study does not establish that claim on the basis that this paper has published no results. None. We'll get to what they actually were in a minute, though.
CO2. This unbalanced buffer dilution results in acidosis.
This study is incapable of informing on cause nor effect, so that's a false statement.
A change in strong ion difference, which is a mathematical construct.
So is your existence, James, still.
Does not cause dilutional acidosis, but is merely a marker for the dilutional process.
This paper is unable to assert that fact. Number 1, because it hasn't produced any data, and number 2, because what the data actually are, which we'll get to in a minute, I really do promise.
Furthermore, we demonstrated that increased water dissociation is not the chemical mechanism of dilutional acidosis.
No, you didn't, you authors of this paper. You didn't demonstrate anything of the sort. Remember, you published no results at all. None.
Stewart's approach does not provide any mechanistic insights into acid-base disorders.
I disagree entirely still. It really does.
The distinction of independent variables and dependent variables by Stewart is arbitrary and depends on the actual regarded system.
Well, if the system that you want to use is known physics, objective reality as we understand it, then you'll use Stewart's model because it is correct in that regard. And then when we make observations and test the model, it's correct. Absolutely correct. Still, I think we're done. But James isn't for some reason. That's right, because he's in full cope mode.
So, however, Stewart's approach is disqualified.
Says who? The authors of this paper on the basis of providing no data whatsoever? Good.
By the incorrect causal and mechanistic explanations derived from these calculations.
If you use the Stewart model, the fully mature, fully developed model, correctly, and you're good enough at math to be able to use the thing, James, which I doubt, then you'll get the right answer.
They disqualified the Stewart approach in these experiments.
No, you didn't. Still.
They may appear to be attractive explanations because of their simple mechanistic mathematical principles.
They're not simple.
But one must not trade accuracy for simplicity.
And we're not.
Consequently, following these principles very quickly leads to an acid-based understanding and terminology that is not concordant with current models in chemistry.
So it's not concordant with the model which currently holds the center of attention in some people's minds. It's therefore wrong. It's a problem, therefore, because it's not concordant with what's already believed at that point. Whoops. That's some good sciencing. Let's ignore things that supersede our science, because our science is the best science. And this newfangled stuff, it's no good because it doesn't agree with us. Oh, well, that makes some good... That's some great sciencing there, James. That's awesome. Well done.
And that might also be beyond the interpretation Stewart originally would have appreciated.
Well, you can't ask him. He passed away a number of years ago, unfortunately. I think he would appreciate where others who have used the lock and key that he provided us with to start this journey, I think he'd love what we've done with it, personally. Anyway, that's for another day.
It is important that quantitative/mathematical correlations must not be directly transformed to real mechanistic processes.
Well, who's doing that? The Stewart model isn't. It seems that most of the delusional theology is coming from you, James.
Therefore, in our opinion, the Stewart approach...
Let's see that? In our opinion. Good.
...leads us to a more differentiated view on the metabolic part of acid-base disorders and allows detailed quantifications that may be helpful in clinical practice, but its mechanistic interpretations must be rejected.
No, that's false. There's nothing in this paper that says anybody must do anything, and I have not rejected the Stewart model. Neither has objective observation of its tenets versus objective reality. What's next, James?
This paper clearly rejects the fact that...
We understand that this paper clearly states an opinion, yes. However, the exact amount of evidentiary material underpinning those opinions that is published in this paper is none. If ever you want to look at an opinion piece, there we go. That's some great sciencing though, James. You've really proved me wrong.
The strong ion difference does not cause acidosis.
Well, that's an opinion, and it's not inconsistent with the Stewart model, because the Stewart model wouldn't suggest that it does.
No dissociation of water is leading to extra protons, and that bicarbonate...
That's not been established by this study or any other.
is not a dependent variable, it is an independent variable.
No, that's not been established by this paper or any other, and it's false. Bicarbonate is a dependent variable.
So I think it is very clear from these experiments.
No, because an experiment has a result. That result being the outcome variables, some actual numbers, James. Where are they in this paper? They're not still.
Both the dilutional experiments, both the in vitro experiments, that Stewart approach is not explaining actually what is happening.
No, that's false. This paper does not show any such thing at all. No.
In regards to acid-base balance.
No.
In the body.
No. Right. So there it is. I'll tell you what though, because James hasn't done his homework, it's important, I think, that homework ought to be done. So I have done. You look at the paper, and these so-called results that the paper is so-called making opinion statements about suggest, you need to see this supplement for the actual results. It's not in the paper. You have to go to the website, which they say is available to authorized persons. Luckily, I'm authorized. So given that the numbers are available to such authorized persons like me, let's have a look at them to see whether or not the data is supportive of the conclusions that were made. So here it is. We're going to zoom to page width so you all can see better. Alrighty. So this is simulation number 1. The results of their computer simulation of a pretend thing that didn't actually occur according to their program that they put together to tell it what to say. None of the assertions in this table have been tested against any mixing of anything in test tubes in a laboratory, any real stuff at all. So we can ignore this table completely. This is simulation number 2, which is only of any value precisely because for this one they did a laboratory procedure to see whether what they get is matched by what they predicted in their model or whether it isn't. If it is, the model is complete, and we must accept this data as being valid. If it's not, we're done, aren't we? Let's have a look at it. Well, looks like reality is not in line with the predictions made by the model. Ergo, the model is incomplete. You'll also notice that no statistical analysis of the differences between the observed values and the predicted values has been undertaken by these authors, let alone the data actually published in their paper. Oh dear. But absolutely, James has proved me wrong. Taken me down, he has. Right, let's have a look at the third one, where there was a comparison. Oops, looks like we missed again, so the model is incomplete. Let's look at number 4. Oh dear, missed again, didn't we? How about number 5? Nope, missed again. So, I think we're done, James. The score is now James minus 50 billions. Yours truly, this bad bald man, 10 out of 10 so far, because I actually read the paper, James, and I traced the rabbit to the bottom of the warren, and I went and got the results that these authors didn't bother to publish. And I had a look at them, as now has everybody else. And what they're now doing is laughing uproariously, side-splittingly. And you're the butt of their jokes, James. Please stop. You are embarrassing yourself, son. All right, so the rest of you, join me next time when someone else will be wrong on the interwebs, but not as wrong as James, because, well, that's a special kind of wrong, isn't it, kiddies? See you then.